Hi, if you can find your way to your seats, please. So, for the second session this morning, we have Andrei Moroianu from CNRS and Saclay telling us about locally conformally product structures. So, Andrei, can we do, 35, 40? Up to.
Thank you,
11,
Enrique.
40.
So I would like to thank the organizers and the Simons Foundation for the invitation. It's my first time in Rio. And I will report on some joint work with Viviana and Adrian, both here, on locally conformally product structures, mainly on quotients of Lie groups. So this work is related to holonomy in the sense that it's about Weil structures with special holonomy, and my first part will be to explain in more detail what is a Weil structure and so on. At the end, we will see that the holonomy in question is in fact a Riemannian holonomy, but on a non-compact manifold. So everything I will say is based on this article, and let me start with the Weil connections on conformal manifolds. So first, what is a conformal structure? Conformal class is just an equivalence class of Riemannian metrics with respect to this equivalence relation. So what is a Weil connection? In conformal geometry, we don't have the Levi-Civita connection, but we still have torsion-free linear connections, which preserve the conformal class in the sense that when you differentiate it, you get a certain one form times the metric for some metric in the conformal class, but actually for any metric, because if you multiply G by a function, a positive function, you just modify the one form theta G. This one form is called the Lie form of D with respect to G. So in conformal geometry, what you fix is the conformal class and some Weil connection, and then the metric G is variable. The metric G has no particular meaning. What is here important is D. Whenever you pick a metric, you also have this one form, which changes when you change the metric according to this formula, which is completely obvious from the definition. And another remark, if this Lie form vanishes, that means exactly that the G is parallel, and so D is the Levi-Civita connection of G. If the one form theta is exact, you see that you can find a function such that for the new metric, the new Lie form vanishes. That means the new metric, if theta is d of phi, you take f to be minus phi. So that means that e to the minus phi g has vanishing Lie form. So d is the Levi-Civita connection of some other metric in the conformal class. So we can now define closed or exact Weil structures by the fact that for some metric in the conformal class, the Lie form is closed or exact for some metric, but of course from the previous slide you see this is independent on the metric. And also that is equivalent from what I said to D being locally or globally the Levi-Civita connection of some metric in the conformal class. So in fact, working with exact Weil structures is just working with Levi-Civita connections, and working with closed Weil structures, this brings some new features because you only have local Levi-Civita connections, local metrics. So if you are on a compact manifold, a closed Weil structure brings some new information. There is a causal formula which relates the Weil structure to the Levi-Civita connection for any metric. So if you take any metric, you have this formula. If you know the Levi-Civita connection plus the Lie form, you have the formula, explicit formula for the Weil structure. That means from here you see that any two of these three objects, the connection, the metric, and the Lie form, determines the third one. So if you have theta and G, you have D, and for the metric, it is determined up to a constant. I now assume that my Weil structure is closed but not exact. We can pull back everything to the universal cover of M. When you pull back a closed form to a simply connected manifold, it becomes exact. So you can write the pullback of theta as d of phi. So from what I said before, the pullback of the Weil connection now has exact Lie form. So it is a Levi-Civita connection of this metric of e to the minus phi g twiddle. Moreover, the fundamental group which acts discretely on the universal cover acts by homotheties of this metric. Let me just show this very quickly. So if you take any gamma in the fundamental group, it preserves the lift of the Lie form by definition. So you can write down gamma star of d phi is d phi. So that means that d of gamma star phi minus phi is 0, assuming, of course, M is connected. That means that gamma star phi is phi plus some constant C gamma. And so you see that the new metric, this metric, HD, is not really preserved by pi 1 because every gamma in pi 1 preserves G twiddle, but it is preserved up to a constant, up to the constant e to the C gamma. Conversely, if you have some simply connected Riemannian manifold with a discrete group of homotheties, then the metric itself is not always projectable on the base, on the quotient with this group, but the Levi-Civita connection of the metric is preserved, so it determines a closed Weil connection on the quotient. So we can say that there is a correspondence between closed Weil connections on the base and Riemannian structures of on the universal cover with discrete groups of homotheties. So in fact, if you like, a closed Weil connection is just a Riemannian metric on the universal cover together with this action by homotheties. So from now on, I will assume that the base, that the manifold M is compact, and that the Weil connection has special holonomy. This Weil connection is still closed and non-exact. So that is, from what I said, is equivalent to the universal cover having special holonomy and a co-compact group of homotheties. Now, remember the Berger-Simons holonomy theorem. So we have three cases. for the holonomy of the Riemannian manifold M twiddle endowed with this metric defined by D. It can be an irreducible symmetric space, but in this case, the scalar curvature is constant, non-zero. So we cannot have any strict homotety on such a manifold, because homotety preserves the Levi-Civita connection. It will preserve the curvature, and so the Ricci tensor. But when you trace the Ricci tensor with respect to the metric to get the scalar curvature, this trace is no longer preserved by the homotety. On the other hand, a constant is always preserved by pullback. So there is a contradiction if the constant is non-zero. So this case cannot occur when our Weil connection is closed but not exact. You notice that I can apply the Berger-Simons holonomy theorem because our connection is locally Levi-Civita. I could not apply this if the connection were non-closed. Second case is the Berger list. So I divide this Berger list into 3 parts. Again, I assume I have special holonomy, so I do not put SON in the list. Well, the blue groups are all subgroups of the unitary group. So the first 3 items correspond to the case where the metric HD is scalar. And in fact, on the base, on the compact base, which will be endowed with some Hermitian structure, this exactly corresponds to LCK geometry. So this is a well-established domain of subdomain of Hermitian geometry. I will not talk about this today. Then the second case, this quaternion-Kähler case, is ruled out by the same argument, because here the scalar curvature is constant and non-zero. And the remaining 2 cases, so they are Ricci flat. So they can occur in principle, but now there is a result by Paul Todd, who was already mentioned by Claude before. What happens here is that if our metric HD has this holonomy, so it's Einstein, that means that the connection D on M, on the compact manifold M, is Weil-Einstein. Weil-Einstein, I will not explain what this is, but in the closed case, it corresponds exactly to the corresponding Levi-Civita connection to have Einstein curvature. And the result of Paul Todd says whenever you have a compact manifold and a Weil-Einstein connection, then with respect to the Gauduchon metric, on the base, the Lie form is dual to a Killing field, but in the closed case, the Lie form is parallel. So if the Lie form is parallel, when you put the Gauduchon metric on the base manifold, that tells you that in fact your base is almost S1 times a nearly Kähler 6 manifold or a nearly parallel G2 manifold, and the metric upstairs. So if you lift the metric, this product metric, if you lift it and then you modify it conformally to get the metric HD, you will get a G2 metric or spin 7 metric. And this, I think, I'm not sure if this construction, this cone construction is due to Robert, but I discovered it in an article by Christian Bell. So we can say that these two cases are also quite well studied, and it remains a third case when the universal cover has reducible holonomy. So what happens here? So this case is much less understood, and so it will be the object of my talk. So I give the following definition. The terminology comes from LCK geometry, locally conformally Kähler geometry. So it's the LCP, or locally conformally product structure, on a compact manifold is just a conformal structure, a closed non-exact Weil connection with reducible holonomy. If you replace reducible holonomy by the fact that the holonomy representation is complex, then you get an LCK structure. Equivalently, from what I said, an LCP structure is just a reducible Riemannian metric on a simply connected manifold and a discrete co-compact group of homotheties. And I asked not all of them to be isometries because I want the connection to be closed and not exact. So it seems like we don't have anything new. We just have a reducible metric and some group, discrete group acting co-compactly. But in fact, this condition is very strong. It turns out it's not easy to construct examples of such structures. So first, I thought to this problem with Florin Belgun, and at that time we thought there are no examples at all. And we have tried to prove this, and we proved that if you have a compact manifold, a closed, non-exact, and non-flat Weil structure, and together with some extra assumption which we needed for the proof, we thought it was just technical, but at the end it turned out not to be just a technical assumption. Then the holonomy is irreducible. And then later, Matveev and Nikolaevsky came up with an example. So the example is very simple. It's on a three-dimensional manifold. Take any symmetric matrix with integer values in SL2Z, for instance, 2, 1, 1, 1. You diagonalize this matrix over R and denote the dual basis of eigenvectors by E1, E2. And then you define the following metric on R2 times R plus star. You take, so T is the parameter on R plus star. So you take E1 squared plus T to the 4 E2 squared plus DT squared. This metric is a reducible metric because you see this factor has nothing to do with this factor. So it's a sum of two Riemannian metrics. This is a word product metric. And now, what is we have to find a group of homotheties which is discrete and co-compact. So we take the following group. We take the translations by integer vectors in R2, and we also look at this map, which maps a vector and a number T to the matrix times the vector, and you multiply T by lambda. First of all, you see that the translations are a normal subgroup in gamma. So, in fact, gamma is a semi-direct product. And when you take the quotient of the manifold by gamma, you can first take the quotient by the translations. So then what do you get? You get the torus times R plus star. And then this matrix A has integer coefficients. So it descends to a diffeomorphism of the torus. And then on the R plus star part, you just have like a sort of translation. So the quotient will be a mapping torus of this diffeomorphism A. So the quotient is compact, the group is discrete, and moreover, you can see that each element in this group preserves the metric, because the translations clearly preserve the metric, and you act by, when you act by the last element of the group, you multiply here by lambda squared, here you multiply by lambda to the 4 times lambda minus 2, and here by lambda squared. So overall, you multiply each term by lambda squared, so it's a homotety. And therefore, the quotient, which is compact, is a S1 bundle over, is a T2 bundle over S1 and has an LCP structure induced by this metric. So the LCP structure is the Val connection, which is the projection of the Levi-Civita connection of this metric to the base. Other examples are so-called Oeklaus-Thoma manifolds. They were introduced in the framework of complex geometry. They are very interesting examples of complex manifolds without Kähler metrics, which do not admit Kähler metrics. And it turns out that for some values of the parameters, when they are defined by means of number fields, and if you only have one real embedding of your number field in C, then these manifolds are even LCK. But in fact, it turns out that they are also LCP in the same time. That, by the way, there is a open problem to study LCP structures which are in the same time LCK. And notice that all these OT manifolds are, in fact, I don't define them, but I just tell you they are solved manifolds. So they have a structure of quotient of a solvable group, very simple solvable group by a lattice, and that motivates us to study LCP structures on solved manifolds. So this is the last thing, general thing I would like to say about LCP manifolds is that the universal cover of the manifold endowed with this metric, the Riemannian metric, is never complete. Is never complete because you have strict homotheties. So if you have a contraction on a complete manifold, you would have a fixed point, but the fundamental group acts without fixed points. So you cannot apply, although this manifold is simply connected, there is no global Durham theorem. There is no decomposition theorem. You only have two parallel distributions, but no global Durham theorem. However, a few years ago, Kurganov proved the following striking result. The universal cover of any LCP manifold is not only a global product, but it's a product of one factor which is flat and one factor which is irreducible and non-flat. So you see already that in contrast to what happens in the Riemannian case, here any such reducible metric, provided it admits the co-compact group, discrete group of homotheties, then you cannot have more than two factors in the Durham decomposition, and one of them is flat and non-trivial. So the situation is, you can see it's already very, very rigid. Some other recent result by Brice Flamancourt says that every homotety in the fundamental group acting on M-Twiddle has algebraic factor. So the homotety factor is an algebraic number. This is, again, in contrast to what happens in the LCK case where there is no obstruction at all. So as I said, we were tempted to study LCP solved manifolds, motivated by the fact that all known examples, including the one I gave from Matveev and Nikolaevsky, are in fact solved manifolds. So let me start with some definitions. A Riemannian Lie group is just a Lie group with a left invariant Riemannian metric. And of course, if you restrict this metric to the Lie algebra, this determines the metric all over the group. And so most of the time, we will identify a left invariant metric with just the scalar product on the Lie algebra that it defines. And more generally, we will identify left invariant tensors with their values at the identity. Like here, for instance, a left invariant 1 form is just an element in the dual of the Lie algebra. The form is closed as one form on the manifold if and only if its restriction to the derived algebra is 0. That's a trivial consequence of the formula for the exterior derivative of theta applied to left invariant vector fields. Now, the Levi-Civita connection of the metric, if you take two left invariant vector fields and you differentiate one with respect to the other, you get another left invariant vector field. So in fact, you can define an algebraic operator, which we also call nabla G, which goes from the Lie algebra to the orthogonal endomorphisms, to skew-symmetric endomorphisms of the Lie algebra. And this is, you have the explicit expression given by the Koszul formula, except that you don't have 6 terms like in the general case. You only have 3 terms because you work with left invariant vector fields, and then 3 of the terms in the usual Koszul formula vanish. Now, for every Lie algebra, we can define the trace form. The trace form is given by this formula. It's just the trace of the adjoint action of each vector. This is not always 0, but we always have that the trace form on a commutator, so by definition is this. You can write by the Jacobi identity, add of xy is the bracket of add x, add y. The trace of a bracket is, of course, 0. So that means that Hg vanishes on the derived algebra, which is generated by such elements. And so Hg is closed. But it's not always 0. We define Lie algebra to be unimodular if the trace form is 0. And Milnor has noticed in 76 that if G has a lattice, that means discrete co-compact subgroup, then the Lie algebra has to be unimodular. It's unfortunately is not going the other way around. So it's only a necessary but not a sufficient condition. Finding sufficient conditions for existence of sorry, I didn't say what is G. This G is the simply connected Lie group associated to the Lie algebra. And so finding sufficient conditions for existence of lattices in general Lie groups is a very hard problem. It's completely out of reach. Now, let's consider some Riemannian Lie group with a left invariant metric, and C, let's denote by C the conformal class of this metric. Every Weil connection can be expressed from the Koszul formula in this way. So it's the Levi-Civita connection plus this tensor that I denote by theta twiddle. We already saw this formula. And if the one form on G is left invariant, then we call this file connection left invariant. And this will be the object that we will study. So let's now choose a closed one form on the Lie algebra, and so on the group, and consider the corresponding closed file connection. We have also a curvature, which is defined like that. Again, this r theta is actually is just an algebraic operator, but when you translate it by left translations, you get the usual curvature operator of the corresponding connection. A subspace of the Lie algebra is called d theta parallel if it is preserved by d theta. So this is very intuitive. And it is called d theta flat. So if it is parallel and if the curvature vanishes on it. So for every x and y in the Lie algebra, for every z in the subspace, this curvature term vanishes. So now I define our first goal is to define LCP structures at the level of Lie algebras. So we define a locally conformally product Lie algebra to be a quadruple given by a Lie algebra, a metric on it, one form, and a subspace U. So this is a metric Lie algebra. Theta is a non-zero closed one form, and U is a d theta flat subspace of the Lie algebra. Non-zero, so we don't want to define a trivial structure. So assume that we have a Riemannian Lie group and a lattice. We can consider, a lattice again is a discrete co-compact group, so we can consider the compact quotient of the group by the lattice acting on the left. As I said, every element in the tensor algebra defines by left translation a tensor on the group. And this tensor is left invariant, so in particular is preserved by the lattice, so it can be projected on the quotient manifold. Now we have the following proposition. If we consider, so in this setting, we look at the Riemannian group, and it has a metric and one form like before. We project them down on the manifold M, which is the quotient of the group by the lattice. And then this pair, so this metric and one form, determines a Weil structure because the metric determines a conformal structure. Theta, as I said, together with G determines a Weil structure, a Weil connection. So this Weil connection is LCP if and only if there is a vector subspace of G of the Lie algebra, so such that this is an LCP Lie algebra. So we have a very simple criterion when we can obtain LCP structure on the quotient of a Riemannian Lie group whenever the Lie algebra has such a structure. So now, if we want to study LCP structures on such quotients, it is enough to study LCP Lie algebras, and then in a second, after maybe classifying them, we have to study the existence of lattices in these algebras. This is our main objective, to study LCP structures on compact Riemannian manifolds, as I said before. So now I concentrate on LCP Lie algebras. Remember, LCP Lie algebra means you have a metric, you have a non-zero one form in the dual of the Lie algebra, which is closed, so that means which vanishes on the derived algebra, and you have a d theta flat subspace. Then we have the following criterion. This is an LCP Lie algebra if and only if the following conditions hold. First, this flat subspace and its orthogonal have to be both Lie subalgebras. Next, we have these two formulas. Here, U is a vector in the subspace U, and X is in U perp. And so you have these two formulas. The interesting thing here is that that will determine, so by taking traces here, you can determine the restriction of theta to U and to U perp just by taking a trace here in X, here in U. And in fact, that means that theta is determined by the trace forms of the Lie algebra G and the small Lie algebras U and U perp. It's just taking traces, and here you take a trace in X, which is the trace in G minus the trace in U. And here you take the trace in U, which is the trace in G minus the trace in U perp. So you have this consequence that the form theta is determined by the trace forms. And moreover, the map, this map nabla theta, which always, this is, I remind you, it's a Weil connection. So it's not really a Riemannian connection. It doesn't take values in SO, but you have to add multiple of the identity. So it's a conformal connection. So if you restrict this map, you remember that U is preserved by nabla theta. So if you restrict it to U, you get this. So this map has to be a Lie algebra representation. It goes from G to some Lie algebra GL of U, and the condition to be a Lie algebra representation is equivalent to the flatness condition. That's not a big deal. So we have this characterization, and then after some work, we get our first main theorem. If the Lie algebra G has a LCP structure, and moreover, it is unimodular and solvable. Unimodular, remember, is a necessary condition for having lattices. So we will most of the time assume unimodularity, although some results are valid without this assumption. But in this case, and if the Lie algebra is solvable, then we have the following two interesting statements. First, this flat space is in fact an abelian ideal contained in the center of the derived algebra, and in fact the derivative with respect to the Weil structure is nothing but the adjoint action when you restrict it to vectors in U. So that's quite unexpected. So that tells you several things. First, that U perp is, which is a Lie subalgebra from the previous slide, is in fact non-unimodular. Well, let me just come back for a while here. Yeah, if you look here, U, the Lie algebra U is, as you see, is a abelian ideal from the theorem. So its trace form is 0. Moreover, we assume that G is unimodular. So when you trace here, you will get 0. You will get a difference of 2 zeros. So that means that theta vanishes on U. And then if you look at the second equation, that shows you that the trace form of U perp cannot be 0. Otherwise, theta would be 0. When you trace here, you cannot, the trace form of U perp is here is the only thing which appears here because G is unimodular. So if you trace in U, is the difference of the trace form in G, which is 0, and the trace form in G perp, which in U perp, sorry, which consequently has to be non-zero, otherwise theta would vanish. And so that means that this H is non-unimodular. And moreover, as I said, so you have an abelian ideal, and the adjoint action on this ideal is just nabla theta. But nabla theta takes values here. So in fact, G is just a semi-direct product of some non-unimodular Lie algebra acting in such a way, so almost orthogonally on a flat space, on a flat Lie algebra, abelian Lie algebra. Conversely, conversely, we have the following proposition, and here we don't even need the solvability. So take any unimodular Lie algebra with non-unimodular metric Lie algebra, so with this trace form, and suppose you have a Lie algebra orthogonal Lie algebra representation which vanishes on the derived algebra. For instance, you can take beta to be 0. Then you add to this beta a multiple of the identity, which is given by this funny constant of the trace form. So this is closed, so that this alpha is still a Lie algebra representation, is immediate, and then you on the semi-direct product of your Lie algebra with RQ, where you have the representation alpha, then you get by taking just the sum of the metrics for any metric on H, and for this one form, which is with this constant times the trace form, you get LCP structure. Moreover, the algebra that you constructed is solvable if and only if H is solvable. This is pretty obvious. So in some sense, you can use this to, this is not a classification, but is a complete description of how you get LCP Lie algebras, starting from a non-unimodular Lie algebra together with some sort of representation satisfying these conditions. So corollary, there is a one-to-one correspondence between unimodular solvable LCP Lie algebras and triples like that of made by a Lie algebra, non-unimodular, a metric, and such a Lie algebra representation vanishing on H prime. In particular, any non-unimodular metric Lie algebra is a codimension 1 subalgebra in LCP Lie algebra. Just take Q equal 1 and beta equal 0 in the corollary, in the previous corollary. So we have now a criterion for existence of LCP structure on any given unimodular Lie algebra. So if you can find a non-unimodular subalgebra and an abelian ideal such that the two of them are in direct sum, and the direct sum is the original algebra. And moreover, the adjoint action of H on U vanishes for every vector in H prime. And if there is a scalar product on U such that this object is skew symmetric for every x in H, where theta is this multiple of the trace form of H, then for every scalar product on H, you have a non-degenerate, we have to skip this as something else, LCP structure on G. We can use this criterion, for example, just consider this 5-dimensional Lie algebra with these brackets. So and we can check that this admits an LCP structure. So we first have to find a subalgebra and an abelian ideal. The subalgebra, if you look at the brackets, you see that E2, E3 is an ideal, and E1, E5, E4 is a subalgebra. So we have H E1 is a subalgebra, E2, E3 is an ideal, and now what is the action of the subalgebra on the ideal? Well, E1 acts by this matrix. If you look there, you see immediately this. E4 doesn't act at all on E2, E3, and E5 acts by the identity. So by the criterion above, this is a Lie algebra where the trace form, we take the trace form of H, which is, we compute it is E5, and then we check just the fact that the restriction of the adjoint action satisfies the condition to be orthogonal when you subtract the multiple of the form theta. Well, I don't expect you to check this, but it's a very simple algebraic check. Now, what about lattices? So we understand perfectly, at least in the solvable case, how LCP Lie algebras look like, but when do they admit lattices? So in many cases, at least in small dimensions, the solvable LCP algebras that we obtained by the above construction are almost abelian. So they have a codimension 1 abelian ideal. And then there is a very nice result by Bock, which gives you a necessary and sufficient condition for the existence of lattices on the corresponding simply connected groups. So assume that you have an almost abelian Lie group, so a semi-direct product of R acting on Rn minus 1 with this Lie algebra. And so here, this Lie algebra means that you have this vector B acts on K by some matrix which we call add B. And so the corresponding group admits a lattice if and only if in Rn minus 1 you can find the basis and a non-zero real number such that this rho of T0, which is the exponential of the adjoint action, this rho is in fact here. It's the action of R on Rn minus 1 at the level of groups. Well, this has to have integer coefficients. This matrix has to preserve, in fact, the lattice in Rn minus 1. And one can even say what the lattice has to be in this case. Well, using these results, we could classify all solvable LCP algebras in dimension less than or equal to 5, where whose corresponding simply connected Lie groups admit lattices. Here, I have to say that this sentence is wrong because of this. So in English, we should say this. So that's I learned from Enrique. So, so there are, in dimension 2, there are no interesting examples. In dimension 3, the only LCP Lie algebra is this one, which is in fact the Matveev-Nikolaevsky example I described at the beginning. It's not completely obvious, but yeah. And of course, it admits lattices. In dimension 4, if you look carefully, you have one decomposable Lie algebra, which is the previous 1 times R, and there is no problem there. And here, all the 3 other examples are almost abelian. So we can apply Bock's criterion. And here, there are lattices. Here, there is a parameter P. For these 2 cases. Here, the Bock's criterion says there is no lattice. And here, for some values of P, which one can describe explicitly, there are lattices.
So P is a real number. These coefficients are real numbers.
Yes, P is a real number satisfying some conditions to avoid repetitions.
It can be real.
Real, yeah. And you just write add of E1, you see, is a matrix, explicit matrix, and you have to say when the exponential of this matrix times a number is conjugate to an integer matrix. So a condition is that the characteristic polynomial has to have integer coefficients, and that imposes conditions on P. And by the way, the set of P for which you have lattices is always countable. So for most P, you don't have lattices. In dimension 5, well, of course, I don't expect you to check this, but you see, in some cases, we have no lattices. In some other cases, whenever we have families, we don't have lattices except for some particular values of the parameters. And that's the end of the classification in dimension 5. And yeah, so just to finish, there are some last-minute developments. In last weeks in Campinas, we worked with Viviana. We obtained an extension of the structure theorem. This decomposition is semi-direct product in the general case, non-solvable case. We also got examples of non-solvable irreducible LCP algebras with simply connected Lie groups admitting lattices. So we get new examples more general than the OT manifolds with LCP structures. And maybe more about that next month in Le Ricci for people going there. Thank you very much.
Thank you, Andrei. Perfect timing. We now have time for questions, comments. Yes, please.
So, are there any examples of LCP structures that don't come from the solved manifold?
From solved manifold. I once heard somebody saying almost all manifolds are solved manifolds. So we have to be precise, yeah. Actually, it's hard to formulate such a problem because it could be a sort of hidden solved manifold, and you, for instance, something which I didn't say is that whenever you take an LCP manifold and you take a Riemannian product, so you take a metric which is adapted in some sense, but I didn't explain this. Take a metric which is adapted on the LCP manifold. You take a Riemannian product with any other manifold, compact manifold. Then this is, again, LCP, and probably non-solvable in general. So first of all, we should assume that the manifold is reducible in some sense. And besides these obvious examples which are non-solvable, I don't think we have non-solvable examples, but it would be, yeah, in some sense, hard to check that they are non-solvable. But we don't have any non-solvable examples. No, sorry. No, we don't have examples which are not quotients of Lie groups. Yeah, of course, we have non-solvable examples since last week, yeah.
What's the lowest dimension?
I think it was 10. It was 10 because you need, actually the radical of your algebra is again LCP. So if you look for the smallest algebra which can act is SL2, and it will, yeah, you need many dimensions, so 10 is the smallest dimension. We were quite surprised. At some point we thought that it is not possible, and at the end we managed to get this example.
Do you want to add? Yes.
No, there are some which are not almost abelian, but fortunately Bock, relying on some other constructions of other people, constructed lattices for these examples because they are still semi-direct products of R2 with R3. So they are almost abelian. this thing of constructing lattices is quite new for me. I'm not at all a specialist, but it's a whole world. It's incredible how hard it is to construct lattices in Lie algebras as soon as they are a bit complicated. If they are not almost a billion, it's, yeah. I don't even know, maybe there are people in the room who know, if in a product of Lie groups, let's say a product of simply connected Lie groups, if you have a lattice, if and only if you have lattices on the two factors. I don't even know this. Maybe it's true, but yeah. In semi-direct products is completely false. There are semi-direct products which admit lattices, but not semi-direct products of lattices.
We still have time for someone to answer the question? If not, we can thank the speaker again.
Thank you.